This lecture is about estimating the natural log of x, and the natural log, as you recall, is a useful transcendental function. So let's get started. And we'll start kind of thinking about specifics. So we want to find out an approximation for the natural log of 2 before this is all over. And in order to do that, just recall the natural log of 2 is equal to L of 1, 2, where L we defined in terms of partitions. We're now going to, in order to get our approximation, we're going to define something, a similar function called U with respect to a partition. So given a partition P, let A equal x naught less than x1 all the way up to xn be equal to b. Let that be a partition of AB. And define U sub p of AB to be the sum from 1 to n of 1 over x sub I minus 1 times x minus x sub 1. So whereas my L sub p's were rectangles that were below my curve, my U sub p will be a sum of rectangles that are above the curve. Note that it's not difficult to see that my UP of AB is going to be bigger than my LP of AB, and we don't even have to look at the pictures to do that. We can just look at the formulas and compare, because 1 over x sub I minus 1 is greater than 1 over x sub I. Okay, so let's get some basic results about that compare U and P. The following statements are true. If Q is a refinement of P, then U sub Q of AB is less than U sub P of AB. So in other words, if we take our partition finer, the U's get smaller. If Q is a refinement of P, then LQ of AB is greater than or equal to LP of AB. And so if we take our refinement finer, then my L's get bigger. 3, for any partition P and Q of AB, U sub P is going to be bigger than L sub Q. Okay, so my U's are just always bigger, okay, over the same interval. And for any partition P of AB, L sub P of AB is less than or equal to L of AB is less than or equal to U of AB. Okay, we'll now go through the steps of proving this. Okay, as has been mentioned before in this course, one method that we have is to kind of sweep our difficulties and take care of that in a special case, and then take the general case after that. So we're going to start here so everybody can concentrate on what the difficulties truly are by looking at a special case. We will first suppose that Q contains exactly one more point that is in P. Okay, in that case there are real numbers x less than z less than y, such that x and y are consecutive points in P, and x, z, y are consecutive points of Q. Okay, and then we calculate, okay, our U sub P of AB minus U sub Q of AB. Now, as U sub Q and U sub P are both sums of basically the area of rectangles, and they match up on all points except these three, when we take the difference, everything falls out except for these three rectangles. Okay, I have the area of the big rectangle 1 over x times y minus x minus the area of the sum of the area of the two smaller rectangles that are kind of contained in across that interval. 1 over x, z minus x plus 1 over y, y minus z. Okay, now let's work out the arithmetic on this. We take that 1 over x times y minus x is equal to 1 over x times z minus x plus 1 over x times y minus z. We can toss this in to the first term and see that our difference here turns out to be 1 over x minus 1 over y times y minus z, and that's a positive number. And so u of p AB is greater than u of q of AB. Okay, now the general case is where q has finitely many more points than p. Then there are partitions p sub I of AB for I equal 1 to n, where p sub 1 is p and p sub n is q. So we can just kind of build up our partitions 1 point at a time from p to q, and such that, again, p sub I plus 1 has exactly one more point than pq. And then we can just apply the special case in a chain here, so that we can see u sub p1 goes down to u sub p2 goes down to u sub p, and I typo anyway. And so therefore we have that u sub p of AB is greater than u sub q of AB. The proof of part 2 follows the same pattern. Okay, so if you work through, I guess it would be a good exercise for you to work through doing 2 following the pattern of 1. Okay, now in order to prove part 3, let's just take any old partitions P and Q of AB. They don't necessarily have to be related to each other. Now let R be equal to the union of P and Q. R will be called the common refinement of P and Q. And so what we can do here, it just rolls out. LP of AB, is made finer by LR, so it's less than or equal to. All of my L's are less than LR. L sub R is going to be less than U sub R, and then U sub R, since it's a refinement since R is a refinement of Q, will be less than U. So bang, bang, bang. We've set up our dominoes right, and they all fall. So this brings us to our point here of approximating the natural log of 2. And so we have an inequality. L sub p of 1, 2 is less than or equal to L of 1, 2 is less than or equal to U sub p of 1, 2. And so so putting in the definition, we have an approximate value of the natural log of 2 as being between LP of 1, 2 and UP of 1, 2. And so for finer and finer partitions, we can get closer to L2. So let's start out with a partition that just has 5 points in it, and just calculate. This is something that you can do with your calculator. And so LP of 1, 2 is 533 over 840. That's approximately 635, 0.635. And if I do it for my u, that's 319 over 420, which is approximately 0.76. So, there's some leeway in there. We don't even have one decimal place. Now, if I take a computer, not doing it by hand anymore, take a computer and do a partition with 101 equally spaced points, we get that the natural log of 2 is between 0.690653 and 0.6956053. So we have 2 decimal points there. Okay. So, not bad for so early in the game. The last 2 slides, we're going to set up for something that's ahead of us. We're set up for the concept of a continuous function. And I wanted to do it again in terms of approximation. And so let's suppose that we have a number a that's bigger than 1 and a number x that is within a distance of a minus 1 of a. Okay, so we're going to say it's not getting too close. Okay, too far away. If x, then let's suppose x is bigger than a, then the natural log of x is equal to L1x, which, because x is bigger than a, we can break it down into this sum L of 1a, L of ax. Okay, and so this first one is natural log of a. This other is just, its area. I can subtract, natural log of a from both sides. When I do so, I get a positive number. I'll put an absolute value around this just because I'm trying to get a formula that's symmetric. And so the distance of the natural log of x from the natural log of a is never any bigger than L of ax. And we can do a similar calculation. If x is just a little smaller than a, we can, again, an absolute value, get the absolute value of the natural log of x minus the natural log of a is less than L of xa, with the values x and a switched around, but because to keep this positive. Okay. Now recall that for a less than b, I have 0 is less than L of ab is less than 1 over a times b minus a. So this means that if for my x bigger than a bigger than 1, I can say that my L xa, a positive number, is less than 1 over a times x minus a, which is less than x minus a. Again, this is a positive number. If a is bigger than x is bigger than 1, I can do a similar calculation and show that L of xa is less than a minus x. And so in general, it follows that the absolute value of natural log of x minus the natural log of a is less than the absolute value of x minus a. Okay, now suppose that 0 is less than a is less than 1. What we do, we find a number n so that n times a is bigger than 1. Then for x close to a, we may calculate that the absolute value of the natural log of the difference is equal to the absolute value of nx minus na. Okay, but we can also calculate that the natural log of nx minus natural log of na is equal to natural log of x minus natural log of a, and so we can get that the absolute value of the natural log of x minus the natural log of a is less than capital N times x minus a. And so again, we have an inequality on how far the natural log of x can be from the natural log of a. What this gives us is control on the function. Okay, we can take this transcendental function, which is quite difficult to calculate specific values of, and we can get a control on how far it wanders in terms of algebraic functions and just arithmetic. So this will be handy. Put a pin in this. We'll talk about it more later.